we might make a start. Welcome everyone for our next CFIGS special seminar series. This is where we try to get some of our eminent experts to give us an update on their recent research and give a little bit of time at the end for some questions. So today we're pleased to welcome Brett Harris from Geophysics to talk to us about fibre optic and sensing technologies for understanding our groundwater resources in this state. So, Brett, thank you very much.
Yep. All right, so I noticed Chris changed my objective saying in this state, but whatever. I actually have got some reasonable examples, but yeah, so my objective today is to sort of give some global context for the research we're doing and bring that down to actually a state and a West Australian perspective and more precisely a southwest of Western Australia perspective. But again, starting with that global challenges that are being faced basically in most countries. So serious global challenges. So if you go to the next one, and the primary challenge that we're all confronted with is daily access to reliable, low-quality, low-cost, high-quality water. So each one of those things is important. So it has to be low-cost, and it has to be reasonably high quality, or at least fit for purpose. So that last bit is an interesting one because we have the technologies now to take relatively low-quality water, i.e. seawater, and convert it to fresh water. That does open doors in some places, but the challenge is for all $8.4 billion. So that's the big scale message. This is me, Sanj, and his mate there in southern Mongolia. This is not far from Oyu Tolgoi, and that mine alone needed many tens of millions of litres per day, I think close to 100 megalitres. Again, it's an environment, and this was, again, a big picture to remind me that the technologies we're going to focus on are going to be basically in-hole technologies. But I'll make the connection to the other typical surveys we do. So if you flip to the next one. Okay, so this looks a bit complicated. So really, we're going to look at the global problem of drought, subsidence, and dry land salinity. And I'm going to make it a thread through to two technologies, very specific technologies that we've been working on. One we have a patent application out of, which is hyperspectral EM logging, and the other one is fibre optics, but there's lots of applications for fibre optics, but I'm going to focus on fibre optics for recovering or characterising chloroelastic properties, but in a simple kind of way, it's the compressibility. So we'll work through why compressibility is important. I've got a soft rock and a hard rock example. And the soft rock example is where we're looking at aquifer compressibility, and the hard rock example is where we're looking at bedrock aquifers and how to find bedrock aquifers, which are notoriously difficult to find. I'm going to look at some conventional technologies because sometimes we get lost in a specific application and forget that the technologies that we are developing at their root are able to provide valuable information to confirm what we routinely use and technologies that are highly effective for groundwater. So this is just our standard EM, GPR and magnetics, and 2 and 3D seismic propagation. Okay, now 2 examples are from Southwest. One example is taken from here, which is literally Curtin University. We've got 900-metre research well, so we'll take one example from there. The other example is from a southwest hard rock site, which is Kojna, and it's part of the Water Smart Farms project, which I'll say a few words about. So if you flip it to the next one. Okay, so this is a project which we did with the Department of Water and Environmental Regulation. This is north of Perth. The width of that image is around 45 to 50 kilometres, and we're looking at a window below the surface where we've done 2D seismic, and the 2D seismic was to characterise the Ballymena fault because it was a significant hydrogeological feature, and it did a fantastic job at that. We have done other jobs where somebody has interpreted a fault between 2 wells that might be 3 or 4 kilometres apart, and it's been there on the map, and we've gone out and done the seismic and clearly demonstrated that it's not a fault, it's just simply a dipping layer between two wells. So the seismic reflection works. We also at Benya, which we'll have a look at later in a different context, which is a aquifer replenishment site, we did probably one of the first full 3D seismic surveys on the planet. It's a very compact survey, about 450 metres by 450 metres, and it did exactly what it was intended to do. It identified an aquifer, the leadable aquifer, that's the principal aquifer the water has been injected in, and it showed that it was extremely boring. It was a sand and clay aquifer, and the permeability of the sands ran to something of 150 metres per day. That's around 150 darts. It's enormous compared to any oil and gas reservoir or most aquifers. So it was a fantastic aquifer to inject into, and it was characterised across that site, and so immediately that site became a great place to re-inject the water that was being produced at the treatment plant. So it didn't have to go anywhere, so it was able to be done there. So that was another really fantastic and success. And the purpose of the seismic wasn't to show exciting geology, it was to show incredibly boring horizontal flat layers that the modelling could be based on. So there's two applications, large-scale application of seismic to find a significant fault that would impact on the large-scale hydraulics, and also a small-scale example, which I haven't shown here. On the side here, we can start to see some of the results from the airborne EM. So we've got the saline water interface. So as the heavier water from the ocean sits below the fresher water driving in from the land, we get a geometry called a seawater wedge, and the airborne has been able to give us an approximate version of that along the coast. In some places it goes in more, in some cases it doesn't, and it's all sorts of reasons for that. Again, beautiful applications of large-scale geophysical methods. So the next one. Okay, for building a hydrostratigraphic model, one of the key things is the clay seal or clay sheet distribution, sand sheets and clay sheet distribution. So they need to be accurately positioned. So this is the result from an airborne EM survey where we've got the distribution of different large-scale clay sheets. The thing that's kind of interesting in this one is that there is a hole. That hole was clearly picked up in the airborne EM data, and that hole allows water to translate or to move between our shallow superficial aquifer, the leadable aquifer, and the Yarraville aquifer. So it was, again, fantastic for building the hydrostratigraphic model that is the basis of the groundwater flow model. The groundwater flow model is used to predict the behaviour of the groundwater system from different groundwater abstraction or different climate change scenarios, so it needs to be accurate. So again, the EM works exceptionally well. And you'll see all these little pencil-like things. So of course they're the wells, and the pencil-like things are coloured. And so you can see the red where the clays are. So the airborne EM is correlated extraordinarily well with all of the clay sheets. And that's what it does well. What it doesn't do well is find things under clay sheets, and it doesn't particularly perform well at finding sand or even clay distributions if you've got a thick upper clay sheet. So use it for what it does well, and basically interpret everything else based on the wells. But I mean, it's a fantastic start. All right, so if we move to the next image. The other technology which is fantastic, but moving now to a hard rock setting, is magnetics. So the great thing about magnetics is that it is essentially about the volumetric distribution of one mineral, which is magnetite. And magnetite, which we'll see, is strongly affected by the distribution of faults, and our bedrock aquifers are dominantly associated with faults. So we'll see how we've used that distribution of magnetite and its expression within the magnetic images like this to basically identify aquifers with a high level of precision and certainty. We've got some arrows there that show remnantly magnetized faults. They're blue, they're on the order of 500 kilometres long, and we kind of pointed to these and said, well, if we are consistently finding water along these structures, then we've got a huge opportunity for water supply, distributed water supply. We're not talking about high volume per well, but we don't need high volumes per well for farmers. But as a long-term, resilient, secure water resource, well on a farm is an excellent option. It is integrated with other options as well. And again, we've got all these beautiful technologies that allow us to desalinate water that's brackish to fresh water. And there are significant advantages to doing that. So long clear structures, the airborne mag, not suitable for targeting by itself, and we'll have a look at why. We need evidence for future targeting to get our percentage of targets that result in a production well as high as possible. So we're talking previously about 1 in 20. Numbers can be juggled according to what you call a good result and bad result, but really 5% success. And our latest work has looked at 50 to 75% and even higher depending on how you define what success is. Okay, so this is part of our water farm set of projects. Again, it's a fantastic coordinated approach to a resilient water supply and management for our future for the wheat belt. So we go to the next slide. Okay, so first we're going to take the thread of this soft rock story right down to the new technology. Okay, but I don't want you to forget that all of these technologies that I am putting up have a basic outcome that contribute to characterising the subsurface for airborne EM, for seismic, for 3D, and for magnets. Okay, so go to the next one. Okay, so the big and simple story from this Nature journal article is that there are locations around the planet that are sinking, and if we look at the orange colour bar, or the orange of the colour bar in the top there, so we see it's greater than 5 centimetres per year of subsidence. We've got massive areas in China that are sinking. We've got very large areas in California that are sinking. So it's a very simple message. We need to understand subsurface compressibility and mechanical properties better. So properties we haven't really ever thought about before. We thought about porosity. We thought about permeability because they are fundamental to getting things or fluids in and out of the subsurface. But mechanical properties have not been considered at these large scales. So if we go to the next slide. Again, this is, and I want to bring in the idea of drought versus abstraction. So the question is the land in these places like California, which says between 2015 and 2022, there is of the order in places of 2 metres of substance. That's not a good look. So there needs to be some careful thought processes. The top image talks about drought and the severity of drought. Did the drought induce more pumping, or is the drought just by itself simply removing water from the system so it's got less load on it? Is that basically relating to the ground subsidence? Again, they're questions that need to be answered. So if we go to the next image, now we get to Western Australia. And that's a really interesting case. And this is, I think, Nick Jinks is the author on this paper. And it's all the outcomes for this site are in part related to the Benya injection site and the fact that at that site there is significant injection of water, up to 45 million litres per day. So if we go through each one of these pictures, we see on the left at the top, cumulative injected volume. Okay, so we've got, of the order, 20 gigalitres injected between 2018 and 2020. So 20 gigalitres injected into the leadable, and around 5 to 10 gigalitres injected into the Yarragadee. Remember, this is a relatively small site. These wells are within 400 metres of each other. And I think there's in the leadable 3 wells. And the leadable's injecting about 3 to 4 times as much because there's 3 wells as opposed to 1 well in Yarragadee. Okay, and so what has happened to the pressure head? So that's the head of water. That's the pressure that the aquifer is under over those period 2018 to 2020. So we can see in the top image where I've written AM27D, which is a well which is reasonably close to where the water is being injected, that the change in head has been of the order 30 metres. We expect it to be reasonably high because it's very close to the injection wells. You can see that the change in head in the Yarra D is less because there's less water being injected, but relatively speaking, it's still higher between 20 and 30 metres. So if we go down and have a look below, we can see AM27 and AM20C and AM27D, which of course have the same ground movements because they're measuring the displacement in the same location. So AM27C and AM27D are in the same location basically. And we can see up to 15 millimetres of ground displacement at that location. Well, that's a lot, but the key thing is that it follows the pattern of injection. Fantastic, it's following the pattern of it, that's what we expect. We basically pump something up, it gets bigger, that's reasonable. However, when we move away from the injection site, let's go to AM75, the story changes. And what we see is we have a reduction, or where we would expect to see a decrease in pressure, we see an increase in pressure in AM27. This is this location over near the coast. And the red is where we see what we expect to see, an increase in aquifer pressurization. And that zone is kind of focused around the injection site. So why would we see an increase in one place and a decrease in another place? So it's quite distinct too. And so people have come with lots of conclusions like, oh, there must be a fault between those two zones, but then why is one going down and one going up particularly as a result of this injection? But the point I'm getting to is that there are three aquifer levels. There's the shallow aquifer level, which will change in terms of pressure, more depending on rainfall. There's a second leadable, which at Beanyap sits at about 100 metres to 200 metres. Then there's the third aquifer level. These are all completely sealed from each other. The third aquifer level starts at about 360 metres and goes for over 1,000 metres, but it's lower permeability than the leadable. So which system is contributing to what we see here? So how would we possibly, we don't have any way of this. All this is done from satellites and also surface measurements. So we don't have a way of understanding how the system is expanding or contracting below the ground. So again, I've set a little structure up. So yeah, doubt or abstraction. What about mechanical properties below the Earth? So if you go to the next one. So we have a well that goes through all of these aquifers. It goes through the shallow aquifer, it completely goes through the leadable aquifer, and it also goes through the Yarra D aquifer. So we're going to be talking about the Yarra D aquifer. And fortunately, when this was built in 2015, we were clever enough to put a fibre bundle. So that's a bundle of fibres. We have multi-mode and single mode. Multi-mode for measuring very accurate temperatures, single mode for measuring distributed acoustic sensing, but really it measures the rate of change or we can recover the rate of change of strain along the fibre's length. So we have 2,400 metres of fibre attached to the outside of a 250 millimetre FRP, fiberglass reinforced plastic well. The well goes down 900 metres, so it goes in a loop, so it goes down and up. So we've actually got two lengths of fibre, and remember in that fibre bundle we've got 12 fibres. So we could, I think there's 12. We could connect it to 12 interrogators, and we should measure different things on each one. Okay, so go to the next slide. And so I guess you've been asking, what does that look like? Well, we've got the fibre bundle loop going down into the hole. And what we're doing is on the picture on my left, we are attaching it to the outside of the 156-inch fiberglass reinforced plastic casing. But you'll see in the casing we've got some slots. So we deliberately slotted the last 240 metres so that would be an interval where we could communicate with the formation through fluid pressure. Okay, so then on this side we can see NADA. NADA develops the one of the interrogators that we use. And he's helping us to put the fibre in. He helped us to basically do the initial testing. So if you go to the next slide. Okay, and these are looking at some results. I'm going to spend a little bit of time on this slide to basically explore what Matt Becker from California State University, Roman Kevsner, and I designed and did in the well. And what we were after is distributed poroelastic properties, but let me simplify that down to how was the compression and expansion of layers distributed in the Yarra Deep. We would initially model and expect that the compression was the same right throughout the aquifer. Okay, so we can see our 900 metre well in the centre there, and up the top, what we have is a plunger. And that plunger was connected to a mechanical device which allowed us to oscillate its level in the water. So the water level in our well is about 23 metres. But if we put the plunger down into the water level goes up about 1.5 metres. So we displace about 1.5 metre of water in the well. When the water level goes up, of course the pressure in the water column goes up and the water flows in through those slots to the aquifer. What we are going to get to is we're going to measure the differential strain rate that occurs when we increase the pressure head. So the little kind of grey cylinder there is what we put in the hole, and we can see the little red arrow is how much the head goes up. It's just a schematic. And down the bottom of the well, we can see our slotted interval. The slotted interval is sealed above and has gravel pack on the outside, and we can see the red. That is our fibre loop that sits on the outside of the fibre reinforced plastic. And we can see some different layers. We have lots of different layers. I mean, often people model things in hydrogeology as being similar properties. But in detail, there are huge variations in the hydraulic and mechanical properties. We've basically got clay and sand and various versions or mixtures of those two things. Even different clays will have different properties in terms of compressibility. So I'm getting there. The bottom image is the water level measured with a standard pressure gauge. We can put that pressure gauge anywhere in the water column and it will look like this when we look at the rise in head. The rise in head is just expressed as metres of pressure. And so at 1040 on this day, we basically just pulsed the plunger in. We just dropped it in. And within a few seconds, the head rose. In this case, to about 1.5 metres. And then we just left the plunger in and we simply allow the water to run into the well. So of course it's going to run into different intervals in the well depending on their permeability. So what we're looking at in terms of the response is the strain rate in terms of nanometers per metre, which is the strain, per second. Okay, so we can see at its peak, the greatest strain rate was of the order 40 nanometers per metre per second. But the interesting thing here is that we have different strain rates. And so we have one formation which has a negative strain rate. At the same time, that our red zone has a positive strain rate. So what's happening? One layer in this aquifer is expanding and another layer is squeezing, which again makes sense because there's vastly different material properties throughout that interval. So we do have some limitations, and I'm not going to talk too much about the detail, but we had set our interrogator with a strain gauge, or with a gauge length of 10 metres. That means that our strain rate is recovered over 10 metre intervals. We can move that 10 metre interval down at 10 centimetre intervals, but we're always getting a strain rate, so it's rate of change of strain from the fibre in 10 metre chunks. And our layers, we know from multiple logs, are much smaller than that. So we're getting a kind of collective response. So we do have interrogators now that can go down to 3 meters or even less, and so I think that'll be an interesting exercise for us to follow through on. But the result from this one is absolutely clear that we do have distributed mechanical properties, and those distributed mechanical properties are going to relate to the compressibility of that formation. How they relate to long-term compression under long-term reduction in head from pumping or increase in head from pumping is yet to be determined. But at least we understand better now how the formation works. So if you read the paper, there is another subtle detail on this as to whether, and this came out of the paper and our work, as to whether the process is an elastic process in the sense that when we inject water, are we able to pump that water out in exactly the same way, but in reverse, and reverse the properties? And so one of the conclusions we came to was that perhaps this is not true. Perhaps some things are irreversible. So you go to the next slide, which is why we did this oscillating test. So we just basically increase and decrease the head repeatedly with our big mechanical wheel that sat on the surface. It just lifted our tube that was reasonably heavy in and out. And we ended up with the black line being the water level and the red line being the strain rate at 232 metres, and then we've got another strain rate at 773 metres. And again, we'll notice that they're completely different. So we're having a reasonably complex relationship between change in head and the change in the properties of, or in the strain rate, which reflects changes in properties in the medium. Okay, so we provided this kind of definitive evidence for something that people had kind of not fully understood because it was extremely difficult to measure. But once you start measuring things, then it kind of opens the floodgate to how we translate the characterization into poroelastic properties and into mechanical properties that may have implications for the way we understand ground subsidence, which is the result of the subsidence that is occurring in multiple layers. So we go to the next slide. So let's have to jump to another technology. How long have we got?
5 or 10 minutes.
5 or 10 minutes, that's right. So the other quality of water is its solute concentration, but we also need to know a stand in play. So I'm going to just quickly go through another technology that we're developing, or have developed, because we have a patent application that's been in play for a year, and we will likely put applications in multiple countries over the next few weeks to months. So if you go to the next slide. So this is a Minex CRC technology. We have built these devices from scratch. So we've got this funny little board down in the corner there, and that is over significant time, so several years developed into prototype devices, and those prototype devices are intended to do something that no other tool can do. So if we go to the next slide. Okay, so I'm going to have a quick attempt to explain what induction logging tool does. We have 2 coils. One is a transmitting coil and one is a receiving coil. So if I go to the top panel that says AC current, when I transmit an AC current through the transmitter coil, what happens is all the charges move a little bit forward, that's 90 degrees, they stop, they move back, that's 180 degrees to the middle, then they move back to 270 degrees, and then they move back to where they started. That's a full cycle, 360 degrees. So our map, the red line of the position or the charge movement with time is the red line on our diagram there. If we make a measurement of voltage in the receiver, what we'll recover is the green line. There's only 2 things that are different between the green line and the red line. One is that it's smaller in voltage, which makes sense, and 2 is that it's delayed. Everything else about it is exactly the same. So the phase offset from the transmitted voltage is one measurement that we can make, and the amplitude is another measurement we can make. So it so happens that the bigger the phase offset, the higher the conductivity of the material that the device is in. Okay, so we can relate the phase offset to the conductivity of the Earth. That's kind of easy. But the other thing we can do is relate the amplitude to other EM properties like magnetic susceptibility. So we get a comprehensive result for the movement of charge in the Earth induced by the movement of charge in our transmitter. And go to the next slide. Okay, so what is different about our tool? Our tool sweeps through a very large number of frequencies, and each frequency gives you different information content. I've got 3 minutes to finish. I'm not quite sure I'm going to make it, but if you go to the next slide. Okay, so that's our patent, so we can move on from that. So the patent is incredibly exacting and long. It's got hundreds of pictures. It's just a painful and painstaking process to write it that takes a long time. So if you like, you can read it. This is one of the pictures from the patent, was modified. But what I'm showing there is results from our well. So we've got a Mount Sopris instrument, completely independent tool operating at a single frequency, 100,000 hertz on the panel 5. On panel 3, we've got our phase offset measurement. So we call it a residual phase offset or calibrated phase offset. And we've got a phase offset for 79,000 hertz. It's just arbitrarily selected, and one for 39,000 hertz. But then we've got the phase offset converted to conductivity, which, because they're in the same position, we'd expect the formation to have the same conductivity, almost the same conductivity, because no two frequencies will investigate the same volume of it. But then they match reasonably well, and they match well with the Mount Sopris instrument tool. Of course, the Mount Sopris instrument tool has a 50 centimetre distance between the transmitter and receiver. It's slightly different, slightly smooth. Our tool slightly higher resolution, probably a bit higher resolution, because it's got a 20 centimetre offset, and we operate at a different frequencies. But on the whole, it's giving almost identical values. So we're very confident in our ability to recover what a commercial tool would give. And what you can see over here is an unprocessed residual phase difference map between 40,000 hertz and 80,000 hertz. Again, go to the next one. And what we would end up with is a conductivity map. So this is an apparent conductivity map. So I've converted our phases to apparent resistivity. In reality, if my phase offsets are correct, I can go straight to an inversion package and get true subsurface conductivity distribution. This is an apparent resistivity map. So this is across the spectral range, 40,000, 70,000 hertz. I can pick anything from 10 hertz up to a megahertz. It's just for our logging purposes this worked. So if you go to the next one. Okay, so now I'm going to jump to a parallel story where we use those two technologies but in a hard rock environment. And this is part of our Water Smart Farms project, bedrock aquifer identification. So if you go to the next slide. Okay, a big picture showing the distribution of soil salinity that is expected around the planet. It's a serious problem. Again, you can look up and verify that from this Nature Communications paper. It's a big deal, and it's a big deal for us in the southwest, and especially in the Pilbara, where we're losing land to dry land salinity as the water levels rise because we've pulled out all the trees and replaced it with crops. That's okay. There's a various range of solutions that have worked on. Okay, so go to the next slide. Okay, so here's a couple of pictures of farmers. Farmers have been fantastic with our project. They help us on their side. They're really accommodating. We've never had a problem with a farmer. They understand that water is an important issue, and the research around water is an important issue. So this guy is drastically changing rainfall patterns are reshaping WA's vast wheat belt. And the second headline there is drinking water to be trucked into more than a dozen West Australian towns due to unprecedented dry. Wouldn't it be nice if the farmers had an on-site water supply so that they didn't have to truck water in, which is ridiculously expensive, and you can imagine with the price of fuel and everything. It's not sustainable. They have to do it because they have to keep their animals alive. All right, so we go to the next slide. Okay, so deep in the subsurface, we have hard rock. The hard rock has some fractures. We don't need massive fractures like this. This is enormous, but this is going to generate a lot. By itself, that fracture will generate a lot of water. That's 327 metres below the surface. So we go to the next slide. Fractures occur in all sorts of weird and wonderful ways. So here's some examples from this paper, but depending on the type of rock and the stress orientations, you're going to get fractures forming in all sorts of complicated patterns. So a structural geologist will give you a lot more detail about that, so I'm going to move on from there because I'm not a structural geologist. So go on, there's another picture that shows the pore spaces at a small scale, and the point from this one is that our permeability related to fractures can be highly variable, they can be highly anisotropic, and extraordinarily difficult to tap into. So we go to the next slide. Again, another image of the relationship between magnetite, hematite, and the oxidation reduction process between them, and the different zones of a fault. So I've got my blue arrows pointing to where we've got a transition from hematite to magnetite, and a change in the magnetic properties of the rock. So we go to the next slide. There's our beautiful image of the southwest of Western Australia, and all our lovely, long, remnantly magnetised dolerite dikes, and our positively normal magnetised dolerite dikes, and our structures in all sorts of wonderful directions. We go to the next slide. Okay, so we've got beautiful examples too that on the southwest coast of WA of these dolerite dikes. Well, they're not just single dikes, they're actually dike swarms in most cases. So go to the next slide. And they have fractures in particular locations, in particular in the granite that is flanking the dolerite and at the contact. So not so much in the dolerite itself. Okay, go to the next slide. Okay, so there's some dolerite dikes. I'm going really quickly now. This is just setting things up. So go to the next slide. They're all in different orientations. If we can work out which ones are good for bedrock aquifers, seems like a good idea. But we have a more general and simple idea. So go to the next slide. Our general simple idea is to basically drill through the dolerite dikes and basically in locations where they're displaced by a younger fault. So that's our general idea. And if we consistently conform to that idea, we were wondering if we would consistently be able to intersect open fractures that we can take water from. So go to the next slide. So that's our fault. It's very obvious from the magnetics. This is different resolutions, but not obvious in the airborne. So our background image is airborne. That's what it looks like when you get down to the scale of the farm. You can't target based on airborne magnetics in most cases, absolutely not. And we have two vintages. One has got about 10 metre line spacing, and one has got about 2 metre line spacing. And again, we have some significant and material increase in our ability to specifically target faults where basement is shallow. And again, where basement is shallow, you're not going to get water out of the sediments above because they're hard enough. Okay, so go to the next slide. Okay. So that's our little story about fractures. So next slide. Okay, so here's our Kojanup site where we've got a production well. It was highly successful, and our strategy has been more generally highly successful in almost every production well that we've targeted with a clear model. We have intersected sufficient fracturing to yield over 50,000 litres a day, which is coming from a place where we were successful in 1 in 20 cases. So we've got a good strategy, a good model, and we've got the technologies to support that. We can increase the probability of intercepting water. So we've got a production well, we've got a monitoring well. So this is a site that we also put fibre optics on the outside of the casing. Both those holes are 100 metres deep, and we did it at almost zero additional cost. We just slipped it into the contract, and the driller said, yeah, okay, that's not a problem. I'll just strap it to the outside of the casing when we put the casing in the hole. And that's exactly what he did. So we have fibre optics on every hole we targeted and drilled in the wheat belt. For this project, for this acquisition, it was about collecting fibre. It was about collecting distributed strain rate during the injection of water in the pumping well and during slug tests in the monitoring well to understand how far we can take the recovery of hydraulics and mechanical properties in these shallow wells. So it's just a stepping stone, but again, it's relatively easy to get to these sites. They're fantastic for research. Again, this was a highly successful 10 litres to 20 litres a second. The water was a little bit brackish, but in terms of locating fractures, absolutely perfect. So Constantine, Roman, myself and Murray did the acquisition here. So that's a picture of us there. So if you go to the next slide, these are what the wells look like. They were just left. Fibre optic bundle is very robust. We haven't had a case where we've come along and the fibre has been destroyed or hasn't worked. Our well's been there since 2015, and it is exactly as we deployed the fibre on the day that the well was installed. The same with these ones. We connected up 3 interrogators because when you've got a fibre bundle, you just connect as many interrogators as you have fibres. So each one of these bundles has at least 4 fibres, so we could collect up 4 interrogators, each one set to measure different ranges of parameters, or at least just testing the different parameters or how the different interrogators perform. Interrogators is the device that sends the light pulse down the centre of the fibre and measures the rate of movement of the fibre as the seismic wave or the pulse developed by changing the pressure in the well tank. So if we go to the next one. So this is a test that we've done. Again, I'm going very quickly. This is the pressure from standard pressure gauges with pressure measurements every second. On the vertical axis, we have the level of the water in the well below the ground. So we have the water level starting at 15 metres below the ground, and then we started to pump and we started to put some slug of water in. And you can see we've got a step test, we did a pulse test, basically to see how that would impact on the fibre. We had a recovery period overnight, and then we did some slug tests where we were throwing 100 litres of water into the well to see how the pressure would translate onto the fibre as a strain rate. So very challenging, but worth a go. Next. So this is what the thing looks like in terms of the strain rates. So the white's a high strain rate, and the red in this case is low strain rate. And we're measuring during the time that we're throwing 100 litres of water into the well. So if we've got the water table sitting, in this case, it was 17 metres below the surface. If we throw water in, it takes about 2 seconds. We've got to think about all these timings. So it takes about 2 seconds for the water to go down the pipe and hit the water. But when it hits the water, we've got this low frequency part at the front, which is probably related to the pressure that's created when you pour a slug of water into a 100 millimetre well. So the water is going to be basically compressed as the slug of water goes down, and then as the water hits the top of the water table in the well, it creates all these really high frequency tube waves. So that's what I think is happening. The little box is there at the top is the time where we're throwing the water into the well. It's going down, and you can see the white line there is following about the head change. Because of course when we throw the water into the well and it enters below the water level goes up. In this case it goes up about 6 or 7 metres, and then it will start to go down again as per the pattern of the blue line on the top. There are some particular things about this well. The only 4 places the water can go into the formation are our screened sections, and the screened sections are only 6 metres. So we're really just looking to compare between how water goes in at those 4 screened intervals. So for the future, we're maybe going to think about constructing some wells that are fully screened. Again, there's arguments for and against that in terms of, there's many arguments about it. So we go to the next one. I'm rushing now, and I'm hoping to get finished in the next few minutes. This is what our Minex spectral induction logging device looks like. We just attach it to a winch and lower it into the hole. It's not complicated. It fits easily into 100 mil PVC. Next slide. And again, there's a comparison of the result from our spectral logging tool in terms of the amplitude, which is related to the distribution of magnetic susceptibility on the left, and on the other side we've got DAS during hydraulic testing, and we can see that we've got some specific arrows there. So one arrow result relates to our bentonite seal location. Another arrow relates to the position of the water table. We've got another arrow that relates to a change in the diameter of the well at the top. So we've got some large diameter surface casing, which changes the nature of the tube wave. We can do all sorts of fancy analysis on that in terms of frequency content. Each of those zones will have different frequency content, but we do start to see some of the information around the geology or the hydraulic studies come out. We started, no way I've got time to basically unravel all the frequency content that's related to the potential mechanical or hydraulic properties for this. In terms of the distributed amplitude across frequency from 3,000 Hertz to 89,000 Hertz, it does a fantastic job of characterising the rock across the production and monitoring well. So if you go to the next one, we're just about there. We're able to work out the apparent dip through our spectral induction logging tool with incredible accuracy. Those formations map in terms of the character of the formation perfectly across all of our frequencies. So again, it was the only method we had available that was able to map what we understood as the dip of the Dykes form, the dolerite Dykes form. So if we go to the next one, again, conclusions, fibre gives us velocity. So I didn't talk about that, but fibre is a basic outcome, gives you velocity, which you can marry with any seismic survey. The spectral induced induction logging gives you conductivity. That's a basic outcome that you want from every logging experience with an induction logging tool, but we also are just moving towards recovering mechanical and hydraulic properties during hydraulic testing. And we are also, with the spectral induced logging, moving towards recovering susceptibility and IP, or frequency-dependent conductivity is another way to say IP parameters, which of course are related to our massive porphyry deposits that produce most of the world's copper. Okay, so that's a really fast version with 1 minute for questions. Sorry about that.
Awesome. Thanks, Brett. I'm just checking online if we've got any questions. I guess the other thing that I would point out is you covered an awful lot there, and we will put a video of this up on the CFIGS website so people can view it again at their leisure. Do we have any questions on the floor? No questions. Okay, I've got a quick question. So you talked about a wide range of different technology. Well, two, but okay, so two different techniques, but there is a wide range of other different downhole techniques that can be applied.
Yep.
How often are those multiple different techniques applied together to get an even broader understanding of the geology and the hydrology, or is it a case of just picking one tool and using it to address the question, or are they complementary?
Yeah, I think the you haven't asked the right question.
Quite possibly.
The right question is how much does it cost to deploy each one of those? Because there are an enormous number of technologies that are available. You could apply NMR to every hole. That would be great. You could apply prompt gamma neutron to every hole. That would be great. But these two are extremely low cost. And so that was the whole point of this experience in the wheat belt, is that could we put fibre on all of the holes at negligible additional cost? And it turns out, when there's more than 13, we put the fibre on and it just sits there. It's not going to deteriorate. And we can go back to any hole and recover or design a test that might facilitate recovery of properties. that we otherwise would not have ever had the opportunity to recover if the whole were not instrumented with fibre. And the EM recovers our standard properties, conductivity, but also, and this is really difficult, because you need a different tool to recover IP parameters, and you need sometimes you need a different tool to recover magnetic susceptibility. And even when you do recover magnetic susceptibility, it's a little bit of magnetic susceptibility and conductivity combined together, depending on the combination of the properties in the whole and outside the whole. So the other thing is having the spectral properties enables you to remove the effect of the whole. So the whole, if it's got saline water in, will dominate the signature, and you'll never know what's outside unless you have multiple readings. So I'm not sure the decisive method and the EM method constitute really what you would want. In a case hole, so I've been all of the examples of case holes. So we don't have access to the formation other than by methods. So